Hi, everybody. So we're going to pick up where Professor Bronkoff left off. As I like to do, let's review where we are so we understand the context. So we're still discussing image compression, the idea of reducing the file size of images. And the main concept behind it is to identify sources of redundancy, meaning ways in which the data are essentially repetitive in nature so that we avoid repeating ourselves in a communication and wasting space. So we've so far talked only about coding redundancy. The specific method we learned there so far was the Huffman coding method for variable length coding. Today, in this lecture, we're going to talk about spatial redundancy. Spatial redundancy has to do with the idea that areas of an image that are next to each other are oftentimes very similar in their pixel value. So if you look at a scene, typically, if you look at a region of the sky, the neighboring region of the sky is the same color. And so if we were to describe all the different blue patches of the sky, one after another, we would be repeating ourselves. Better to describe the first patch of sky and then say somehow that the next patch over is similar to that one, and that avoids repeating. So we're going to learn a method of doing that. Now, I'm going to do this lecture a little differently than I would in class because you have the opportunity to pause the video. So I'm going to not write while I'm talking. I'm just going to show the notes and discuss them. And, of course, pause when you need to jot it down. So this is section 7.6.2. Differential pulse code modulation, or DPCM. Now, the idea here is that realistic images are not discrete memoryless sources. That means the pixels are not all independent of one another. If they were, the picture would just look like noise. So most realistic images are more like Markov sources. Don't worry if you're not an expert on that. Basically, all I need you to know is that neighboring pixels may be correlated with each other, meaning similar, statistically similar to each other. and not just image pixels, but also patches of an image. So entire small regions, neighboring regions may be similar to each other. So correlations, of course, indicate spatial redundancy in this case. If two pixels were perfectly correlated, we would only need to transmit the value of the first one, and then the second one we would be able to perfectly predict from the first one if they were indeed always the same as each other. So there would be no use communicating each pixel separately. So that's a very extreme example, which it would not typically happen. You would normally not have a perfect correlation. You would have some degree of correlation. Now, if the correlation is not perfect, you still may be able to predict one pixel from the next. But if in that case, your predictions won't be perfect, and so the error needs to also be transmitted. Now let me back up and make this more concrete for you. So way back at the beginning of this section, I gave a very extreme example where you have an image where every single pixel has a value of 100. Well, in that case, of course, if I would tell you the value of the first pixel, 100, and then ask you to tell you that the remaining pixels are very similar to that one, then what you might do is to guess that all of the other ones are 100, and in that simple case you would be exactly correct, and we would have communicated the whole image with a single number. But now let's back off of that extreme case. Let's suppose that the first pixel is 100 and that the next pixel is 99. So let's say we would have 100, 99, 100, 101. Let's say these were some example pixels. Well, if you used the algorithm we just described, I would first tell you the value 100. Then you, the receiver, would guess that this pixel is also 100. But you would be slightly wrong. So in order for me, the sender, transmitter, to give you a perfectly accurate representation, I would have to tell you that if you guess that this is 100, you will be one too high, because 100 minus 99 is 1. Okay. If you then assume that if this pixel is again 100, after correcting with that scale, I'm sorry, if you guess that this one is 99, because now you know it to be 99, you would then guess that this is 99, and you would be wrong by 1. And for me to correct you, I would have to tell you, hey, if you use this value as the guess for this value, you'll be 1 too low, so add 1. So I would essentially be transmitting the following sequence to you. I would say 100, then you would guess 99, and I'd tell you, you would guess 100, and I'd say, no, it's 1 lower than that. So I would have to tell you minus 1. And then if you use 99 as the guess for 100, I would have to tell you you're off by 1. And then if you used 100 as the guess for this one, I would again tell you you're off by 1. So rather than sending you a series of fairly large numbers which take up a lot of storage, I would send you one large number and then a series of small numbers that simply represent the difference. Okay? So this series of steps here describes what I just spelled out. The steps are that the coder, that's me, the sender, and the decoder, that's you, the receiver, agree in advance on the prediction method. So in my little example, the prediction method was to guess that the next pixel is the same as the previous pixel. The coder then uses that method to try to predict the next pixel value, to get a value x hat. The coder records the error in prediction. So in this case, the error would be 99 minus 100, which would be the guess, is epsilon. So epsilon would be minus 1 in this case. And now to make this method even more efficient, let me back up for a second. So up to this point, this idea that I have spelled out for you is using spatial redundancy. It's using the fact that spatially the pixels are similar to each other. Okay, but now we can go even further and now bring in our understanding of coding redundancy. So what we can do is to have the coder, rather than transmitting the errors in their raw form, we can transmit the errors using Huffman coding. So now we've combined two different redundancy tricks in one scheme. To complete the transmission, the decoder decodes the errors, does the prediction according to the agreed on method, and then uses the decoded errors to correct the mistakes, which are called residuals. So these are called the residuals. All right. So this is a hallmark of the compression field, which is that you bring in multiple tricks to do the compression. So here we've used a spatial redundancy trick and a coding redundancy trick in the Huffman. Okay, so what I described a moment ago was a very simplistic type of prediction. We guessed that the next pixel is simply the same as the current pixel in value. That would be like if you were a weather forecaster and what you did was to forecast the weather. If yesterday was 70 degrees, you would predict that today would be 70 degrees as well. So it would be the most simple sort of prediction. But let me describe a fancier kind of prediction that you should be familiar with called linear prediction. In linear prediction, we try to predict a pixel's value as a weighted sum of its neighbors. So for example, let's say that these are 4 neighboring pixels' values, and pixel, the one with the box, is the current one. In this scheme, rather than saying that this one is simply equal to this one, which is what we did a second ago, we're instead going to assume that it is somehow related to this one, and this one. So the one above, the one next to it, and the one up and to the left. Now, you may wonder, well, pixels have neighbors all the way around. There's one up here, one to the right, down here, 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 right? Why are we not using those? The reason is that if we assume that the image will be communicated in raster method, like lexicographic ordering, then the pixel values will come one row at a time. And when we reach this pixel, we will only know the pixels previously sent. So that would be the one before it, the one in the row above it. We won't have received any of these yet, so we can't use them in that case. So this is called a causal neighborhood. This is called the causal neighborhood of that pixel. Okay, so in the linear prediction, the predicted value of this pixel is a linear combination, a weighted sum of those 3 neighbors, these 3 guys, with A, B, and C being coefficients, constant coefficients. And that's going to be the method. So this would be like, for example, in the temperature example, if I wanted to predict today's temperature, rather than simply saying it's equal to yesterday's, I could say something like it's 0.6 times yesterday's temperature plus 0.4 times the previous day's temperature. So you use 2 previous days, basically drawing a line, a linear trend through the examples to guess what today will be. And that's essentially what this is doing. Well, now, so far, we've described it in terms of just there being some A, B, and C, but we don't know what would be a good way of predicting. So we need to have a method of finding A, B, and C. And the way that we do it is as follows, or one way we could do it is as follows. Let's say we have some example data. Let's say these are some pixels in a similar image or a part of this image. Then we can use each pixel. For example, this x22 is that pixel. Use these as examples from which to learn the relationship. So this is what we sometimes call machine learning or pattern recognition. So what we're saying is, if this relationship here is true, each pixel is related to these neighbors, well then this one must be related to its neighbors in this way. This one must be related to its neighbors in this same way, and so forth. So each is an example of this linear relationship. Well, we see that this is really just a system of equations, and now all the things we've learned earlier in the semester from image restoration and so on can help us once again. That's why I wanted to spend so much time on that particular problem. We see that this set of linear equations can be written as a matrix equation. So we put all the left-hand values in here, all of the neighbor pixel values in this matrix, and we see that writing it this way with A, B, C in a vector is the same as writing these equations. And this can be all summarized by one matrix equation. X is equal to HA. Well, that's no different in form from G equals HF. Remember that from imaging. We've seen this equation over and over again. The form of this is exactly the same. You have a vector, matrix H, vector. And we already know how to solve that, right? So I'm not going to solve it again. I'll just remind you that this is exactly like image restoration, and one way to solve it is using unconstrained least squares. Now, in this problem, if we have enough pixels, I'm sorry, let me go back. If we have enough pixels as examples here, we can have a very overdetermined problem. And if you'll remember in least squares what happened when we had an overdetermined problem, do you remember the example where we had several linear equations and they didn't intersect because of noise? Here we'll have noise too, in the sense that each of these equations isn't precisely correct, because in truth this pixel isn't exactly A times this one, B times that one, and so on. Just as if we tried to predict temperature, a simple thing like this won't be right all the time. It might just be close, right? So really you could say there's like a noise here that we're not writing. So in a way this is really like HA plus N, or G, which would be like our imaging equation, G equals HF plus N. And remember, when we had linear equations with noise, the least squares solution found us a very reasonable answer in the middle. And this is overdetermined in the same way, so least squares is fine. And we know that the answer is the pseudo-inverse. And so here the thing we're solving for is not an image, it's this set of coefficients. Now, I wanted to teach you that approach because it's good stuff to know. But in practice, you may not want to go to all the trouble of trying to estimate those for your individual image each time. So often you settle for some simple combination of the A's, the A, B, C coefficients, such as these examples here. Okay, so I'm going to stop this and we'll pick it up in the next video.